Building a music streaming platform like Spotify is a classic system design problem, and that is because it includes audio delivery, metadata management, object storage, and everything in between that you need to know to design things from scratch. And especially if you're a mid-level developer who struggles to design systems or features from scratch, then this will be very helpful for you. So let's see how we can design this in 7 simple steps. First, we'll start by understanding the requirements and planning the capacity. Then we'll come up with the high-level architecture and the system flow of read and write operations. After which we'll need to design the API and also the storage and database. And then finally, we'll move on to scalability and understanding how we can scale this system for, let's say, 50 million users or above. And at the end, I will also show you the pyramid that separates senior engineers from mid-level developers so that you can understand what are the skills that you need to learn to be able to design such systems from scratch, no matter if it's system design for Spotify or for Google Doc or for any other system. Let's start from understanding requirements as a first step, because without this we cannot move any further if we don't know what we are building here. So we are looking to build a music streaming platform for about 500,000 users, and it will handle over like 30 million songs in this platform. So the core requirements here will be that artists need to be able to upload their songs to the platform. On the other end, users need to be able to search and play the songs that are uploaded by these artists. They need to be able also to create and manage playlists on their accounts. For this, we also need to have a profile for users so that they can maintain their own playlists, and some basic monitoring and observability like health checks for the servers, error tracking, performance metrics, and so on. For audio formats, we will use OGG and AAC type of files, which are just audio file formats that compress the music without losing the quality, and they also take up less space. For example, we can use 64 kilobits per second for mobile data saving and 128 for standard quality, and for premium users we can deliver 320 kilobits per second. And on average, we also need to know the size of these files, like what is the average size of a music file. And let's assume that for normal audio quality, which is the 128 kilobits per second, it is 3 megabytes on average, but this is also something you need to clarify before moving on to the next stage. Once we have the requirements, the next step is to plan the capacity of this system, and especially for song storage, song metadata, and also the user metadata and daily bandwidth that we'll be dealing with. For song storage, since we assumed that 3 megabytes is the average size of a song, and we have 30 million songs that we are working with, this translates to 90 terabytes on average of raw audio data. And this doesn't include the replicas across different regions, which might be duplicates of the same song. And it also doesn't include the versioning overhead when artists re-upload the songs for certain reasons. Let's say they want to change something and they just end up re-uploading the same song. So that's why we will also need to estimate these like at least 2 or 3 times higher than the amount that we have here, which is 90 terabytes. For song metadata, let's say each song needs a title, artist references, duration, file URLs, and so on. So we will need at least like 100 bytes per song to store the metadata on average. And if we assume that it's 100 bytes, then we'll need to multiply that by the 30 million, which will end up being 3 gigabytes. So this is practically like nothing compared to the song storage. As you can see, the main storage that we'll be dealing with in this system is the song storage, which will be an object storage. For user metadata, again, this won't be something huge, like let's say we need to obtain the user profiles, preferences, and playlist data. If we assume it's like 1 kilobytes per user profile data that we'll be storing, and we have the 500k users, which we clarified in the first requirements here, that means that we'll be dealing with 500 times 1 kilobyte, which will be just half gigabytes of storage for profiles. And the fourth thing we need to estimate is the daily bandwidth that we'll be using. The average listen time, let's say, is 3.5 minutes. This is also something that needs to be clarified in the previous step. And if we are using the 128 to 160 kilobits per second, That is roughly 3 to 4 megabytes per streaming. And let's assume each user streams like 10 to 15 songs daily. This will lead to significant egress costs. Egress costs are the fees that cloud providers charge when data leaves their network to reach to the users. Overall, the key insight that we get from the capacity planning is that audio will dominate both storage costs and bandwidth. The metadata is just a small part or portion of this system. So with that, we can move on to the high-level architecture, like a very high-level architecture for now. We'll need to have some sort of mobile app, or let's say the web interface of the application. This will be the user-facing app that handles the UI, the user searches, the playback controls, and playlist management. It will make HTTP calls to the REST APIs, but before that we will have a load balancer that will distribute these incoming requests across multiple API servers. And these servers will be the RESTful APIs. As an algorithm for the load balancer, we can use either round robin or we can use the least connections algorithm. And the load balancer will also make the health checks of the API servers and make sure that they are always available. Next, we have the API layer where we have our RESTful APIs. Here as a validation, we can use JWT tokens and query the database song for metadata and URLs. We'll use an SQL database for storing the metadata, and these servers will be querying it from the SQL database. But for audio files, we'll need some sort of blob storage to store these files, since they are the biggest portion of our system. And these will be queried with generated signed URLs, which is a one-time URL that expires after some time so that we keep the URLs safe and they are not always accessible through the same URL. An example of this blob storage can be like AWS's S3 storage, which is a way for storing large files like the OGG files that we need to store as part of this Spotify design. And this type of blob storages offer virtually unlimited scalability, and it also comes with built-in durability and cost effectiveness for the large files. That's why this is a good solution for storing these type of audio files. With this high-level design, now we can think about the read and write workflows of the system. And let's start from the read workflow, which is users playing a song. So the very first step is user hits the play button and they play a song in the mobile app. This will make a request like get to songs/ID. This is also something we need to design in the API design very soon in the next step. And then after that we'll hit the load balancer, which will route the request to the API server. API server, as a first step, it will validate whether the user is authenticated with the JWT token. And if they are authenticated, then we'll get into this block where we will be starting to play the song. So it will first query the song metadata from SQL database where we store the metadata of the song and user profiles. It will return the song details. Once we have the metadata, we will also generate the signed URL here in the API server. And then we will return the metadata plus the signed URL of the song to the mobile app. Then mobile app will range requests for audio chunks to the blob storage using the signed URL, and blob storage will stream the audio back to the mobile app. Let's say we are also tracking some analytics for each played song. For that reason, we will also make another post request to songs/ID of the song/play to track the analytics, and here we can send the metadata that we want to store for later. And we will return authentication error in case the JWT is invalid, so all of the steps above won't be handled if the user is not authenticated. Next, we have the write workflow of this same system, which is artists uploading a media file, which is the audio file. So the first point again is the mobile app. It will make a post request to store the song with the metadata. And this will again reach to the load balancer first, then it will forward the upload request to the API server. In the API, we will likely have some file size limits, so we will first validate the file format and also the size. And if it is valid, then we will continue with the next steps. If it is invalid, then we will just return the rejected payload with unsupported format or unsupported size of the file. Otherwise, as a first step, we need to store the audio file in the blob storage. So we'll send it to the blob storage which we are using. And then after that, we will extract the audio metadata like the duration, the bitrate, and also the other things which we will get in the post body, like the title of the song and so on. And once we have all the metadata like the song type, the artist, the title, we can insert this into the SQL database. Also, once it is uploaded, we can also move it by hierarchical structure if we want to. Like if we want to store the file inside of the artists, then by artist ID, then the album ID. We can do that also in the blob storage. Technically, the object storages don't have hierarchical structures. This is just an illusion that you have it, but this is also useful for us to keep track of things like they are in a folder format. Then if we are going to use any sort of CDN, we'll need also some CDN invalidation. CDN here will be used for caching copies of the content like artist pages, album metadata, song details, which will be closer to the users for fast delivery. And it will also clear the old cached data so users see the latest songs and artist updates right away. And that will also be used in this request to make sure we are keeping everything up to date in the CDNs. And lastly, we will also send the response to the mobile app, notifying that the upload has been successful. The next step for us will be to design this API and the database in a bit more detail. So let's start from the API design. For the search and discovery, we'll need a way to search different content types with pagination. Let's say user searches for a specific song. We will need to make a request to /search endpoint and provide the query, which will be the exact thing they search for. And here we can pass more details, like if we know that the user is searching for a song, we can pass the type as song. And we'll pass the limit, which can be like 20 by default, and the offset, which means that from where we need to start the counter in the songs. Next, we will also get the trending songs, and optionally this can also be filtered by genre or by some other things. So it will be a GET request to /songs/trending, and then we can pass the additional filters if we want to, and the limit on how many songs we want to query from the API. Users will also need to get all songs by a specific artist. Let's say they are browsing the songs for a specific artist and they want to see the songs only of this artist. For that, we'll need to have an endpoint for /artists/ID of the artist and then /songs, which will return the songs that only belong to this artist, and the limit, as always, to limit the response from the API. Next, we need to also control the content access. The first endpoint here will be to get the song metadata and the URL of the audio file. It will be a GET request to /songs/ID of the song, which will return all the metadata and the streaming URL. We also need to have a direct streaming endpoint like /songs/ID of the song and then /something like stream, which will be an alternative to the signed URLs. And we need to also design for the playlists, since the users can maintain playlists and they will be querying it back, optionally with also the song list that is included in the playlist. So it can be a GET request to /playlists/ID, which will just return the playlist details. And then if you also include the query like include songs, then it will also return the songs that are included in this playlist. Now let's see what are the user actions that we can expect. For example, regular users will also be creating playlists, right? So for that we need some sort of post endpoint to /playlists. As a metadata, we can expect like something simple like just the name of the playlist and whether it is public or only available to this user. Then once they create it, they will be also adding songs to it, which will be a put request to the same playlist with the ID. And then /songs, and here we can include the IDs of the songs, like some new songs that they are adding to this playlist, and the position where we are adding this. Let's say they already have 4 songs in the playlist or 5 songs, and then we are adding from position of 5 or 6, so we will be sending the position along with it as well. Similarly, they will also remove a song from the playlist, which will be the same request URL, but at the end we will also pass the song ID that we want to remove from this playlist. And they can also like or unlike a song so that it is added to their favorites. And that will be done with a post request to /songs/id of that song and /like, which will be maintaining their favorites in the database. And lastly, we'll need some way to manage the users. For example, we will need to fetch the current users playlists with some request like get to /users/me/playlists. And we can also limit this with some limit if the playlists are too many for the user. Similarly, we need the songs liked by the user. So here they are adding it to their favorites. Here we can use like users/me/either likes or liked songs, but whatever we are using here, it will be also nice if we use the same plural here as well, so that it's following the RESTful API principles. And then the limit, which can be like 50 or something else, and the offset where we are starting to retrieve this from. And they need to also be able to follow artists to be notified from their latest songs, which will be done with a post request to the users/me/follow, and then we will pass the artist ID to follow this specific artist. That is it for the API basic design. Now we can move on to the data storage. First, let's talk about the blob storage we will be using. Let's say it's an S3 in AWS, or it can be like Azure's blob storage. We will need to use this for storing the audio files because such large files cannot be stored in SQL or some simple databases, so we need some blob storage or object storage for this. The audio files here are immutable, meaning once you upload them, you cannot change them. So if you need to make a change to the uploaded file, you need to re-upload it and remove the old one. And we can also organize them in a hierarchical structure as we saw before. So we can store them like artist/the artist ID /album/album ID and then /the song ID. This will be easier for us for retrieving the files later. As a database, we will be using some sort of relational database like either PostgreSQL or MySQL. And this is the basic structure we will have in the database. Let's start with users, where we will be storing the user ID and some metadata about them, like the email, the password hash, created at, which will be the creation or like the sign up date for this user, when they last logged in, subscription type and country, and this can be many more metadata, but this is just the bare minimum that we need to have. And with the user ID, we will have a foreign key linked to the owner ID of playlists. So since we will have playlists, we also need to have the owner of which playlist belongs to which user. And we will also have the playlist ID for linking these to the playlist items. We need the name and created at for this playlist. Then each playlist will have some songs in it, right? So here we can use a join table. This can be something like playlist items, which will contain, first of all, the playlist ID and also the song ID and the position, like where is this song positioned in the playlist and when is it added to the playlist, if we need to also maintain that. This will basically be the table that joins the playlists and the songs together. For the songs, again, we will have the ID, which is the most important thing here, and some metadata like the title, duration, and so on. And another important part here is the file URL, which we'll be using to query the audio file to stream it from the blob storage. Then we will also have artists, which we can store in another type of table other than the users for keeping this separate. So we can have the artist ID and then the metadata about them, like the name, country, and so on. And we'll need to connect the artists to the songs. For that, we can use another join table like artist songs, where we can keep track of, most importantly, the song ID that they uploaded and the artist ID, like which song belongs to which artist. And additionally, we can store some more metadata here, but this is the bare minimum that we need to have in this table. And why we choose SQL here? Because we need a lot of joins, as you can see, for playlists and songs, for songs and artists. So this is a natural selection for us to go with SQL type of database. We can do even more complex queries here, like find all songs by artists that a user follows or some other complex queries like that. And that is possible with SQL type of databases. And once the database grows, we'll need to also add indexes for the important properties here, which will be the frequently accessed columns. And in our case, we can, for example, index the title in the song table. We can index the name in the artists table. And we can also index the song IDs in this join table, where we'll be joining the playlists and songs. These indexes will enable us to have fast search capabilities, which will also handle the typos and partial matches that user expects when they are searching for a song or for a playlist. And the playlist item index will speed up the queries when fetching songs for a specific playlist or finding which playlists contain a specific song. That's it for the planning of general object storage and also the SQL database. Now let's see how we can scale this. Let's say the user base grows to 50 million users now and the songs grow to 200 million songs. This means our current architecture cannot handle it more, which means if we calculate the requirements again, we will have 100 bytes for 200 million songs for song metadata. That will be 20 gigabytes. For user metadata, it will be 1 kilobyte times the user base, which will be 50 gigabytes. But for audio storage, you can see we estimated 3 megabytes per audio file. And if we multiply that by the amount of song, which is now 200 million, let's say, it will be equal to something like 600 terabytes. And this is not even including the replicas, the regional copies, or the multi-file uploads by artists. So in reality, this will be like 2 or 3 times more. So let's see how our scale phase might look like. As a first step, we can add CDN edges for different regions of the world. For example, we can have one for North America, we can have in Europe, we can have in South America. This will speed up the process of retrieving it from CDN. And similar to that, we can have load balancers in different regions. Let's say we have at least 2 load balancers in 2 different regions that are still mapping the incoming requests to the API servers that we have. Before getting to API servers, for the CDNs, we need to use some sort of eviction policy for cache management. And here it's a good use case to use the LRU cache method, which is automatically removing the least accessed content when storage fills up. And the cache would fetch from the origin storage on a cache miss. For the API servers, since we are not maintaining any type of user session or any storage, these are completely stateless, meaning we can scale them as many as needed to handle the incoming traffic. So adding more capacity here is straightforward. We are just replicating the existing API servers. The main thing here is that when designing the API server, we need to design for truly stateless servers so that it's possible for us to scale this easily. Next, we need to also scale the database because the single instance cannot handle that many metadata storage, which means we need to separate the reads and the writes in the databases. For the writes, we can use a leader replica where we will be writing the new files of the songs or new playlists that users are creating. But when reading it, we can have some slave or follower databases, which will be only used for reading. So this will be in sync with the leader database. But whenever we get any read operations like getting the song metadata, getting the playlist metadata, we will be reading them from the follower databases. As a next step, if this is not enough, we can also consider sharding the database. Sharding will split the data across many database instances. Let's say we will have one shard for the US users and one shard for the European users. We can split it by geographically, and then we will partition songs by the artist ID ranges. This will give us horizontal scalability and it will improve the performance by keeping the related data together. And also for the blob storage, we can replicate this to be in different regions. Like for Europe users, they will be uploading to a blob storage that is in Europe region. For North America, they will be uploading songs to the blob storage that is in their own region, and so on for the other geographics in the world. And all of them will still be using signed URLs for accessing the audio files and streaming the music chunks. Of course, there are many things that can be improved on this system, like improving the reliability or monitoring, but the key, as you can see, is starting simple. We don't want to over-engineer for small amount of users and then gradually increasing the scale as we go. And lastly, let's see how you can also be able to design such systems or features from scratch and what's the real difference that separates senior engineers from mid-level developers. If you think the designing part as this pyramid, on the bottom, which is the main, like most important part, is the planning, which is the blueprinting phase, the technical design, understanding requirements, as you saw, estimating capacity, choosing the architecture. This is where everyone needs to start when designing such large-scale systems. And only then we move on to the tech stack selection, which is like picking the right database, whether it's SQL or NoSQL, and if it's SQL, then what exact type of SQL database it will be, the caching layers, eviction policies, storage solutions, and all of that tech-related stack selection. And only last stage, which is the most smallest part actually at this designing, is the coding, which is like starting to implement the things. But that is actually the thing that requires the least brain power. And especially if coding is the only thing that you can do, then we have now these cloud or GBT models which can do it faster, better, and cheaper. So what's the point of any company to pay you if the only thing that you can do is coding? That is where the most mid-level developers are stuck, because they have this completely upside down. They start developing things without even having any plan, without having any tech stack selection. They just start coding and see where it takes them. Whereas the fundamental stickers who learn to think through problems before even touching a keyboard or before even starting to build any code, these are the ones that will never struggle to find roles, because all the companies are always in need for such developers who can think through problems from users' perspective and also bring like rough ideas to reality by understanding the requirements, by asking the right questions. So if you're at the first category, which is like you're still stuck in the mid-level, but you want to make the shift to turn into senior developer and start getting paid like one, then I also run a mentorship program where I help developers like you exactly to master these skills. We work on real complex systems, advanced architectures, and also the interview preparation strategies so that we can get you to senior roles and you can start getting paid like a senior developer. And if you're serious about leveling up and making that leap, then the first link in the description is for you, so you can apply there to see if you qualify. And I'm looking forward to seeing you inside.